Okay, so welcome everybody. So it's a great pleasure to have Shruti Karan here, that she can continue.
Yeah, so thank you. I'm glad some of you survived till the end of the lecture series. Before we start today's lecture, I just wanted to point out that I actually forgot to include two names in this list. So I just wanted to say that I also worked with Huan Heng Chi, who is a postdoc in Michigan, and Aiden Herdiske, who is going to be a postdoc starting in fall at the IAS. And if you have the chance to look at what Callum and Aiden are doing, it's really interesting stuff. So yeah, just an advertisement for their stuff. Okay, so today's lecture, in case you weren't paying attention for the first two, won't be that connected with the first two. For one, we will be talking about Yang-Mills. So we're no longer, just dealing with photons. We're going to be dealing with gluons. We'll also particularly only be looking at Yang-Mills, no higher derivative corrections, nothing like that. This construction that we talked about a little bit last time, which was the BCFW construction, the reason that it works is actually kind of easy to see just even from the Lagrangian. And it's that I can't add any more interactions to Yang-Mills over here. Right? That as long as I don't introduce a new coupling. So if I have to have another interaction term that depends on G, then G is my Yang-Mills coupling, then I can't add anything that is both gauge invariant and look. So if I try to add something, it'll just, in 4 dimensions, it'll violate the fact that all of this needs to be the same mass dimension, which is 4. Okay, good. So now, of course, this fact has to be visible from the point of view of scattering amplitudes, right? And the way that that's visible is that
Why do you care about it being mass dimension 4?
Because what do you mean? It's a Lagrangian density in 4 dimensions has to be mass dimension 4.
I could trace n to the 4 and put some.
Yeah, it would involve a dimension-full different coupling from G Yang-Mills. That's all I'm saying. So if I want to only have terms, if I want the only coupling in my theory to be G Yang-Mills, this is all I can write down. Yeah.
You mean that you don't have any other one?
Yeah, yes. Yeah. So good. So now at the level,
you would put different couplings there also.
yeah, so all of these will involve different couplings. It can't involve G. So it will have to be some dimension-full parameter, basically.
Yeah,
the different parameter from G.
It doesn't affect scattering, but perturbation theory, but you could add theta.
Yes. Yeah. Okay. So okay, agree. So let me not let me make then the statement, let me make it perturbative. That perturbatively, this is all you can have. And so then from the point of view of scattering amplitudes, this already tells you that there must be a way of constructing any endpoint amplitude using just the fact that it's a local amplitude and everything has to, on poles, factorize into lower point things. Okay. So this is a sort of heuristic reason for why constructions like BCFW works, right? This is,
I don't understand.
okay. So basically, in terms of Feynman diagrams, the only vertices that I have are at 3-point and 4-point. Okay. So already there you can see that I'm writing down, let's say, an 8-point amplitude only by gluing together 3- and 4-point pieces. Okay. This is already not true in theories like perturbative gravity, for example. Okay. So that's one aspect of it. So now what I'm saying is, if I want to think of this fully on shell and in this kind of way that we've been looking at things, where it's not Feynman rules, but rather amplitudes themselves that we're writing down, I'm saying that if you write down something that factorizes correctly at endpoint, there's no contact contribution I can write down to add to it. Mass dimension.
Suppose we did scalar theory with 5 to the 4.
Yeah.
All your words you could say same words.
Yeah.
But I thought scalar theory with 5 to the 4. But not BCFW.
I think you can still do, maybe not BCFW, but you can do some recursive construction, like some all-line shift will work there, for example.
Right. So you say even for a scalar theory,
Yeah.
5 to the 4 scalar theory.
Yeah. Yeah, I think the problem that, or rather the reason no one talks about that is because the number of diagrams isn't much less than infinite when you're doing finite diagrams. It's not actually
My
helpful.
big point was that BCFW, you get 1 by z because of some epsilon.
Um,
Scalar will just go like 1. Because 5 to the 4 is 1. So how will you?
So
Sure.
5 to the 4, I don't want to say anything too strong because I know that someone has looked at this, but I can't remember what the result is. But I would imagine that, so definitely for an all line shift, right, where I'm introducing Z on every single momentum line, all my amplitudes are going to be 1 over momentum to the power something. And so naturally at infinity, my amplitude is going to die out. And BCFW, as you said, is very specific.
Yeah. Propagator. The
Yeah,
pole is
so-
in the propagator.
Yeah, the pole is in the propagator. And yeah, and 5-4 is just a bunch of propagators, basically. I mean, at the level of the amplitude, it's just propagators.
So I had somehow thought it was important that these amplitudes, just like this,
Mhm.
these amplitudes die faster than 1. So this 1 by z, 1 by z squared.
So okay, that when I'm saying this, I'm not actually this. I mean, this general argument doesn't say that BCFW will work. It says that there must be some way to do this on shell that is recursive for the simple reason that there are no new contact contributions at every order. So all the information is contained at lower orders. So when I say order, I mean in N. So
Lagrangian completely determines the
yeah, and there are only 3 and 4 point interactions. I mean, it's not a very deep statement that I'm trying to make. I'm just saying there are no endpoint contact contributions, which means that everything has to be determined by the fact that there exists only 3 and 4 point interactions.
I'm sorry you told me to say this, but in gravity, what is the difference in gravity?
You have at every endpoint you have terms.
So it's all determined.
It's all determined, which is again, but then you need to have a smart recursion relation, which knows why it's determined, and BCFW is an example of such a recursion
There we
relation.
know that we can add that gravity does not determine the theory up to the non-deterministic because of the non-deterministic.
Uh-huh.
So that certainly is not true that the amplitude is going to be determined.
Sure. At 3 level it is though.
Actually,
Yeah. These are all 3 level statements. Yeah. Okay. Okay. So yeah, this is a bit slogan level, but this is all just to say that we can indeed, I mean, it's natural to expect that you can construct Yang-Mills 3 level amplitudes by just gluing together 3 point and 4 point vertices. Okay. Now actually you can do one better, which is just 3 point vertices. And that's because this term could not have been anything else because of gauge invariance. So yeah, so you can actually just write any Yang-Mills amplitude in this way. Okay, so this is at 3 level. I know this looks like a loop diagram. I'll explain why this is not a loop diagram. It's actually a tree diagram. But basically, the point is you can just glue together fully on-shell 3 point amplitudes and construct things like this. Yeah. Good. And we already saw this a little bit when we looked at BCFW, because BCFW told you exactly this fact, that if I start with only on-shell 3 point amplitudes, I can construct any 3 level amplitude for a Yang-Mills theory. Okay. Good. Now, yeah.
I mean, I agree that 4 point term in the Lagrangian is determined by gauge invariance.
Yeah.
But what does that mean that there is some differential operator acting on this diagram that we show all diagrams with 4 points and
So, I mean, in general, it'll be a sum over diagrams like this. But they will only have, these are the diagrams. I mean, you're not doing anything to them. This is
the diagrams that are 4 points.
the diagrams that have 4 point couplings look like you're sort of blowing up the 4 point coupling into 3 point interactions. And the reason you can do that is because of BCFW and subsets. So, I mean, when I say all of this, I have in mind that you're doing the shift that we talked about last time. So lambda goes to lambda plus v, lambda 1, and then, lambda 2 tilde goes to lambda 2 minus v.
So one
Something like this.
that's happy technique. So just look at the whole exchange in gravity. Okay. And then that's by itself not gauge. And then you ask, What can you add to make it?
So you take the answer and make it.
Sure.
So, but you don't have to do that if you use BCFW. That's the point. This is what BCFW automatically does for you, which is that when I put together two 3-point amplitudes, the thing I get out is gauge invariant already, which means it already includes that 4-point contact term that you would have added if you did find the diagram.
Oh, so you BCFW is looking for the.
BCFW just says that it has good Z behavior at infinity, but that translates to it being a healthy theory. And so actually, yeah, so actually when you do this and you do that contour integral, etc., what you're already building in is that this answer is gauge invariant, even though it looks like it's only a product of 3-point stuff. Yeah. Yeah, so well, I mean, I don't know if you, yeah.
Maybe you work with manifestly gauge invariant.
Yes. Yes. So all of these circles over here, these vertices, all of them are on shell gauge invariant 3-point amplitudes. It's just I've not told you how to specify what are the internal momenta. Yeah. So I mean, this will not be fully determined. There'll be some free coefficients in the internal momenta, and those will be precisely these parameters that you introduce when you start doing this BCFW construction. Yeah. Yeah, we look a little more explicitly where how to determine the internal momenta in a few slides. Yeah. Okay, but okay, so good. One thing about this diagram is that it's planar, and that's always true for 3-level Yang-Mills amplitudes, that you can always write it as some planar on-shell diagram. So this is what I'm going to call an on-shell diagram. They're also called Playbic graphs, so planar bicolored graphs. Yeah. Okay, right at the end, I'll comment on that because there are some things that change. For example, this ordering is a bit difficult because you don't have external ordering. Yeah. But there is a formalism. Yeah. Okay. At loop level, naturally for Yang-Mills, you expect that there needs to also be some non-planar contributions. Okay. Now, mostly people work in the planar limit, so they just get rid of those contributions, but they do exist if you look at the full theory. And in those loop amplitudes, you would have a situation where the cuts will give you these non-planar on-shell diagrams. Okay, so this is non-planar because I can't ascribe an external ordering to 1, 2, 3, 4. Okay. So the aim of this talk is going to be, can I say anything about these on-shell diagrams? Okay, no, tree level. So the point is that loop level on the cuts will give rise to non-planar on-shell diagrams that look like tree-level non-planar on-shell diagrams. So what can I say about those? Yeah. All right. So we'll use two things. One we looked at a little bit before, which was the BCFW recursion relations, and the second will be on-shell diagrams and some auxiliary space formulation of those on-shell diagrams.
So BCFW has nothing to do with the diagram.
No. That's why it works for gravity. So, yeah. The proofs for the behavior for Yang-Mills has something to do with planarity. So, so if you just write this down, this is just some tree-level process. I mean, this is, yeah, I mean this. So, okay, let me say it differently. This would be a loop diagram, which genuinely would be subleading in N. Yeah. Yeah. So, yeah. Now, once I take a cut, I get a tree-level amplitude. But the tree-level amplitude, you know that all tree-level amplitudes are planar. But that doesn't mean that. So, actually, this slide, yeah, here. So, you know that this will be a planar amplitude. But you want to write it as, but you can write this as a sum of non-planar contributions. And only some of these non-planar contributions will show up on the cuts of loops. So
This is very specific to kind of diagram that we're doing, right? These words, they are not to be confused with, from one over an expansion.
So the ultimate aim would be to do the full 1 over n expansion. But to do that, you would have to include, at loop level, you would have to include non-planar contributions.
I think we can clear when you open the small diagram.
Yeah. So, I mean, basically on a loop, you would get something that looks like this. And because people have not mostly worked in the large n limit, they don't have good descriptions of objects that look like this. Yeah. And these
For the final loop.
for the final loop diagram, or rather the loop diagram on a cut. Yeah. So, yeah. So on-shell diagrams tell you what happens on the cuts of loop diagrams. And if you took a non-planar loop diagram, you would get a non-planar on-shell diagram. And people haven't studied these objects much.
I remember 10 years ago reading that integrals for loop, for planar diagrams, wasn't well defined, but less so for object diagrams.
Yeah.
You know what I'm talking about?
So that's kind of the statement that if you look at a planar loop diagram, all of the cuts look like this, the maximal cuts. Yeah. They all look like planar on-shell diagrams. But that is not the case. So once you go to non-planar loop, you get non-planar on-shell diagrams. Yeah. And this itself is not an amplitude. It's just an on-shell object.
And everything else before you do it there, right? Integral.
Yeah, so this talk will just be about these kinds of diagrams. So it won't really be about loop level stuff. Yeah, but the motivation for why you would want to study these kinds of objects is definitely only at loop level, because tree level amplitudes are planar. No, I didn't. I just kind of said there probably exists 3-point amplitudes, but I'll give you the exact definition. Okay, hopefully it will become a bit clearer, but towards a little later, if it doesn't, please ask. Yeah. Okay. So two terms or whatever, two properties that come up. One is positivity and one is holomorphicity. So positivity or positive geometry is like the slogan level term that people throw around a lot. So I want to be very careful about what I exactly mean about this, and we'll define it. And then we'll see whether or not that positivity can any amount of it lasts when you go to non-planar things. Okay. So, okay, as I said, these non-planar on-shell diagrams, they show up in unitarity cuts of loop integrands. And what we want to see is whether nice properties of planar graphs can be can extend to non-planar sector as well. Okay. Now, what has this got to do with BCFW? Well, BCFW just gives me a nice way of writing down an amplitude as a sum over non-planar things. So I'm going to take something that is planar that everyone knows how to calculate. I'm going to break it up into pieces that are non-planar, and people don't know how to write. People don't have a nice way of explaining what those non-planar pieces are. But because I know this side, I'm going to say something about what these individual non-planar diagrams are. That's the logic. Okay. And in particular, we want a geometric way of thinking about these non-planar contributions. And eventually, like the really far goal would be that it's not just the non-planar pieces that come in this sort of tree level way, but all non-planar pieces that we'll be able to explain. Okay. But right now, it's only these that appear in this way, because that gives me a way to understand what these are, because I already know what this is at tree level.
The word planar never appeared in your first image.
Yes. That's because I was either dealing with photons or I was in large N, or basically, or tree level, whatever. Yeah.
It's not indeed one over speed, right? That's what you mean by this.
They would contribute at 1 over n to a loop amplitude. Yes.
So is this, I mean, at the Feynman diagram level, if you have a loop amplitude which is non-planar.
Yeah.
Okay, and you connect it to tree amplitude. Of course, tree amplitude is still a planar. So that non-planarity that would arise by such a cut.
Yeah.
For the tree amplitude, some sort of a fake non-linearity issue.
Yeah, it's
that
not-
affects
it's-
by,
Yeah,
putting the like in appropriate places.
right. So then basically
That's
you're,
kind of-
you're removing some kind of sum that would have given you a factor of n, basically, when you do that cut. I think that is the way, at least that's the way that I think about it. Yeah. Okay. Okay, so one difference also is that in this talk we'll be very supersymmetric, maximally supersymmetric. It's possible to do all these on-shell constructions even just for Yang-Mills. It's just much messier. And so as a first step, given that we were anyway dealing with non-planar things, we decided to do n equals 4. So this n equals 4 super Yang-Mills. I'm going to be on shell the whole time. So I'm going to realize supersymmetry on shell in the following way, basically through a superfield that looks like this. Okay, so this contains the whole on-shell supermultiplet, the gluon, which is in pink over here, the gluino, which on one side I've called psi, and okay, this is very poorly written, I'm sorry. There are a lot of mistakes on this, but basically there is a fermion here, a fermion, same fermion here, or conjugate fermion here, and there should be a scalar here. Sorry, lots of typos. Yes, and eta A is the superspace, on-shell superspace coordinate. I don't know what you want to call it, whether you want to call it a coordinate or not, but it's the on-shell superspace parameter and it's Grassmann, and this A is just this SU4R index. Okay. Sorry? Sorry, where? Yeah, so this capital A is the SU4, the R index. And then the and the little a is the spinor index.
I think you're asking if the index is A or something.
Yeah.
I mean, this one.
Yeah. It is summed
So
over.
in the second term, there is a phi.
Yeah, sorry, there is a phi AB here, and this should also be psi. I'm sorry, there are a lot of typos on this equation. I don't know why. Okay. Yeah, sorry about that. Yeah, you're correct. So this would be like, this is not a valid expression. Yeah. Okay. Etas are, I'm not sure how to answer that. Etas are Grassmann. Yeah.
Is there also just for eta?
No. So this is just eta. I mean, you can, okay, there is a eta dagger, which is like the Fourier transform of eta.
Yeah, I suppose what's confusing is that I'm more used to thinking of off-shell superspace, where there would be an eta and a theta mark.
Yeah.
I don't see any analog of that here.
Yeah, so here you have eta, there is a eta dagger, which is kind of so it's like saying, do I think, it's telling you which side you're thinking of as the Clifford vacuum, which is sort of a choice. So whether I'm starting at G plus and going down this way, or I'm starting at G minus and going down.
It's not even thinking of this. This is just a
exactly. So so literally the super amplitude is now just this nicely book kept thing where it's a polynomial in eta, and different coefficients of eta that give you different component amplitudes.
It's basically a sigma plus.
Yeah. But I will say that of all bookkeeping devices, this is actually a very, very good bookkeeping device, because it allows you to take this out in front. And then what is left over is very, very simple. And we'll see exactly like this. If we didn't take this out, there would be factors sitting out here that would be much harder for us to recreate. Yeah.
What is the relationship between electricity, the amount of electricity violation and the number of etas? Like, why is it like this?
So number of eta, so eta k gives k negative gluons.
Okay.
So eta square is the first order, and that's MHV. Are you asking why that's true?
Yeah, like Yeah, right.
Okay, so two reasons. So the first is that if you look at this, right? If I multiplied this with a constant, there's no way Q dagger could kill a constant. Right? So you have to multiply it with something with enough etas that Q dagger when it hits that gives you 0. Yeah.
Okay, because there's some relationship between helicity and the.
Yeah, because I mean, G minus comes with 4 of these guys, and G plus comes with none. So that's why the order in eta gives you how many of these are there. And sorry, I should have said this. When I say eta square, I actually mean eta 1 square times eta 2 square times eta 3 square times eta 4 square, where 1, 2, 3, 4 are the R indices. Yeah. Yeah. So it is eta 1. So each of these has another index, which is whichth particle this is. Yeah, so gamma, this will be like gamma of, no, that's right. Yeah, that is exactly for every, so there are a lot of indices. There is I, which is telling you whichth particle, and A, which is telling you which. Yeah, so when I say eta 1 squared, I mean eta 1 1 times eta 1 2 or something like that. Yeah, I don't think I give the explicit form. No, I don't. So Q is the charge on shell. So these are representations of Q that satisfy the algebra. And so now I want my amplitude to satisfy Q dot amplitude, and Q dagger dot amplitude is 0. Yeah. And the Q dagger, because it's multiplicative, you can pull out in front of this delta function. And that has eta to the 8. Yeah. And whatever is left over, so Q kills this, but Q won't kill this. So you have to make sure that whatever polynomial comes after also Q kills. So this is just like, yeah, it's just a way of making sure that whenever you're constructing your amplitude, it's supersymmetric. Yeah. Okay. Okay, so I've written this mysterious statement over here. This works well with factorization. So what I mean is the following, which is now if you were to do BCFW, but you would also want to make sure that you're doing this in a way that you only get supersymmetric amplitudes out, right? If you start getting non-supersymmetric stuff, then that kind of defeats the purpose. So you want to also shift the Grassmann variable so that now super momentum is conserved, not just momentum. Okay. So Q is conserved under this shift. Okay. And the only modification to the VCFW formula is that now I have to integrate over the internal eta. So that's basically like saying I want to sum over the full supermultiplet in the middle of this. Okay. Okay. Yeah.
What is this strange thing which looks like a gate for the square value?
This one? Yeah, so that is the spinor helicity variable. So that's just the wave function of fermion of some positive helicity. So you're writing P mu sigma mu AB dot as PA PB dot. So this is the PA part. Yeah. So I will, yeah, so we can call that, I'll either call it lambda or I'll call it angle. And lambda tilde or square. And then you do this is the BCFW shift, the Brito, Kachazo, Feng and Witten shift. And then, yeah, so this automatizes calculating your AN point amplitude. Yeah. Okay, good. So that's okay. So though this is what is going on in the background, I might kind of still write plus or minus, but that's to be taken as the correct eta component of the super amplitude. It's just easier to look at diagrams if it says plus minus on them for me personally. But okay, so good. So now when I do this shift and I'm trying to construct an MHV amplitude, right? So eta square amplitude, then I get only one term, which is the following. Okay. So this over here, let me just write it down so that throughout people can look at it, is NK minus 2 MHV. So K equals 2, which is the pink, is MHV. K equals 1 is, well, N minus 1 MHV, which is MHV bar, which only exists, well, it exists at all orders, yeah. But I mean particularly a 3-point over here, okay. So this is the only BCFW term that you get. And in particular, you note that we don't have these. This one, because it doesn't have a pole on the internal leg, right? Because I've shifted this and I've shifted this, they satisfy momentum conservation. There's no pole from this factorization channel. This one, this amplitude just doesn't exist in Yang-Mills. Okay, good. Yeah. So orange, so the numbers inside are what really matter. So the number is 2, meaning that it's NK minus 2 MHV. So it's MHV. And then 1, it means MHV bar. So that's the 3-point. So only at 3-point does this exist. It's the amplitude with the linear in eta. Yeah.
And wow, sorry, you said something about only this exists. Sorry.
So this is the only term in the BCFW expansion for an MHV amplitude when I shift 1 and n.
Sorry, you said why?
So because if you try and, so obviously, yeah, so you can start trying to move legs there, but then this will happen. Yeah. And if you wanted to move this one on that side, then that's just not a pole. The valid amplitude or whatever, it will be a pole actually in the physical amplitude once I do the, whatever, once I do this procedure. Yeah. But the only BCFW term is this one. Okay. Good. Now, this is the case specifically when I shift 1 and n, because they were next to each other. If I instead chose to shift 1 and k, then there are 2 more possibilities. Okay.
Go back once.
Yes.
Are you indicating here which one positive or which are negative?
No, but I have in mind some which ones I'm shifting the angles and squares and eta off.
Okay, so in that diagram, could I see which ones were the positive and negative?
So one is the square and n is the angle.
So all of those were positive. Sorry, so in the end of the
So okay, if you're thinking of it as positive, negative, right? Then this one is negative, negative, positive, 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 positive.
So there are 2 negatives, both of them there. I see.
Yeah, I mean, okay. Again, this is we're not talking about component amplitudes. So it's some like, yeah, but this is, yeah, that's the thing. So minus, minus, plus, 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 plus.
Yes, and now how did it go with that? That plus at 2 became a minus at 1 when you did the treatment.
Sorry, say that again. The plus at 2.
The intermediate guy between 1 and 2.
Yeah, so this is plus on this side and minus on that side. Yeah, yeah.
Okay, now.
Yeah. Okay, so just to recap, this is, if you want to think of it in helicity components, minus, minus, plus, 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 plus. That's the first one, so that's MHV, and this one is minus, plus, plus.
I thought the number said that it's NK minus 2. Then it's actually
These numbers, right?
Yeah.
Yeah. Yeah, they do.
Right, but you said the guy on the right side, right?
Yes. So it's NK minus 2 MHV. So this is MH. 2 means MHV.
Okay.
Yeah. K is the number of negative helicity gluons that you can get out. Yeah. Yeah.
How do you decide whether to take minus 1 there or minus 2 over there?
This is color ordered.
That's color.
Yeah. Yeah. Yeah, okay, sorry. So this is also why gravity is so much more complicated, because gravity you would have had all of these guys that could be on that side. Yeah. So this is why Yang-Mills is much easier. You get exactly 1 term. Yeah. Yeah. Okay. So you get exactly 1 term if you shift the adjacent legs, but if you shift non-adjacent legs, so here I've shifted 1 and k, you get more possibilities, right? Because now your k is allowed to be with k minus 1, but it's also allowed to be with k plus 1. And earlier you couldn't be with k plus 1 because you were next to the other shifted guy. So you get these 2. Okay. So this is the first example of how if you do non-adjacent BCFW, you get something a bit different from the adjacent.
And you can choose what to shift.
You can choose what to shift. And the whole thing will be that if you choose slightly differently, you get non-planar stuff. You'll see how that works. Okay. Okay, so this is Ronak's question. What are white and black vertices? Good. So I'm going to use this notation where the white vertex is this amplitude over here, which is the amplitude, which is what I called 1 earlier. And it is the, you can think of it as plus, plus, minus. Okay, that's the, it's the MHV bar at 3 point.
Black and white vertex, they are one.
Yeah. No. So you can do it without supersymmetry as well. It's just that this, so over here it looks really simple. And when I introduce W, then you just have the minus of W over here. For the non-supersymmetric case, there'll be some Jacobian in the numerator. That's the only thing, which, yeah. Yeah. But you can do it, you can even do it in gravity. Yeah. 1 second. So this is the plus, plus, minus. This is white. It's a bit confusing on the blackboard, which one you're calling white and black, but this is white, and this is black. Okay. Okay. So, okay, now, so this is the amplitude for Yang-Mills 3 point. That's just what it is. This is momentum conserving delta function. This is the supersymmetry conserving delta function. And this is the what is left of the amplitude after you take away those things. Now I can rewrite this by introducing some auxiliary matrix, which I've called W for white. And yes. It's 3 point. It's like the on-shell. This is just the 3 point amplitude. Yeah. So now, yeah. So you have. I'm going to introduce this W. Okay. The details don't really matter. The point is that I can rewrite this vertex as an integral over some auxiliary matrix. Okay. And the content of this and this are identical. There is nothing extra about what I did by introducing this W. Okay. You can roughly count also if you, I don't know if that's fun for you, then you can count the number of delta functions and see that there is no extra information in W. Okay. Some of it goes away because you have some, I'm dividing out by some GL1. So that takes away one component of W. Okay. Then I know that I have to be left with 2 cross 2 plus 1 cross 4 delta functions. So that's 8. And then you can just do a counting and see that these two are fully localized by the other delta functions. Okay. So there is no extra information. I just want to emphasize there is no extra information in doing this. Yes, there's no extra information. So similarly, you can do this for black. Yes. This one is the super part of it. So let's make sure that's supersymmetric. It's like, it's not exactly delta Q dagger because it's MHV, it looks a bit different. Yeah, so it's eta to the 1 instead of eta square, which is what it is at MHV. So. What, why is it 1 cross 3?
Yeah.
I'm not sure what you're looking for in that answer. I mean, there is a way of writing this. Yeah. So, okay, there is a way of thinking about all of this in terms of planes and what is perpendicular to what, etc. So you can do that. And here you've made some choice by saying that the angles are the people we like and the squares are the people we don't like in some sense. And so you've written this. So that's why the dimensionality of B and W are different. But that's just a function of whether you're thinking of these matrices as living in lambda space or lambda tilde space. Yeah. And you can think of it like there's a geometric way of thinking about it. Yeah. Those are minors of W. Yeah. Maximal minors. So like in this case, it's very trivial. It's just 1 cross 1 minors. But yeah, once we get bigger matrices, it will be K cross N matrix and K cross K minors. Okay. So you can do the same thing with the black vertex, and you have some integral representation where you integrate over a matrix. Okay. Good. So now there is a way of writing your BCFW terms with these black and white vertices. Okay, which is simply that if you have this BCFW term in terms of these black and white vertices, this is what it looks like. Okay, now it's really not very hard to show that these two are equal, but it's just, it's just arithmetic. You just have to say that, okay, momentum is conserved here, momentum is conserved here, momentum is like that, solve all the constraints and see that it's the same as this.
I thought you were saying that it was building up the same amplitude using BCFW for lower point seven. That's not the case.
Well, so this is the BCFW term, right? And this thing basically tells you that there is a BCFW shift between n and 1 by putting this bridge between n and 1.
Sorry, isn't that also a legitimate
This one?
experiment? Yeah. Couldn't I build that original amplitude out of those amplitudes?
Yeah.
Start as the starting point?
Yeah, exactly. So say we were doing 4-point.
Yeah.
This would just be the MHV 3-point. So it would just be a black vertex. So it would just be this.
Yeah.
Then that's it. This is just that one.
So that by itself is a legitimate BCFW representation of final amplitude.
Yes.
So they have to be.
Yeah. So yeah, exactly. So then you take, for example, then at 5-point, you take the same bridge, except now this is a 4-point amplitude. So this just goes in here. Right. Yeah.
The orange thing you said, vertex the left is plus minus, right?
Mm.
Why did that just become a black dot on the?
Because it's a plus plus minus, but it is a plus plus minus with a shifted momentum evaluated on the pole. So it's not n actually, right? This is not n minus 1 something. That is a mistake. So this is just to show you that this is n, Pn. Sorry. So this is just n and 1 on the right hand side. It's not n hat and 1 hat. Z got absorbed in the fact that this is not fully determined, all of the internal lines. So you have one parameter.
The loop kind of thing.
Yeah. So you get one parameter, but I also want to remind you that here when I write this, Z has taken a value, which is the value at the pole. Z equals that Zi, where the pole is. So that will also be implemented by adding this bridge. Yeah. Yeah. A bit of faith involved that it does actually work out, but it works out. And that this implements exactly this. Yeah, where the extra parameter is one of the internal things and it gets fixed by momentum conservation to be whatever it has to be. For this to be the correct BCFW term.
Sorry, just one elementary question. Does BCFW press three amplitudes in terms of trees of these?
What do you mean?
These ones that two?
So this is what BCFW would give you.
It's including the loop.
Yeah, but they are not. I mean, these are everything is fully determined in the stack. Yeah, it looks like a loop, but yeah.
You also said there was some delta functions associated with the vertex, right?
Right.
But if you have a loop, just like diagram logic, there is some undetermined parameter, right?
Yeah. So it turns out that the ones that appear in BCFW, this integral is fully localized, just like it was over here. So all these delta functions, you solve the constraints, and there is exactly one thing this can be. There's no leftover integral. So the ones that have leftover integrals won't be tree level amplitudes. They'll never show up in BCFW. Okay. So
how with the one chose in this 3-point function became the 3-point BCFW thing, one orange dot.
Yeah.
Became somehow weird.
So this weird thing, basically what I'm saying is that if you remove this part of the diagram, right, just the white, black, white part, what it implements is the shift on n and 1. Because here, okay, yeah, sorry, I should have written n and 1 here, not n hat and 1 hat. But basically here it is n hat and 1 hat. You want to make sure that you are evaluating this diagram where this is genuinely an on-shell propagator on n hat and 1 hat, not on. So to do that, you can't just add this as white because that would evaluate it on n and 1, right? So you need something more than just putting a white vertex there, because that would evaluate it unshifted. The shift is taken care of by adding this.
Yeah.
Yeah.
Anything about that? CW will do the same where it takes momentum plus C times Q and Q minus. So then the P, so then these internal lines are sort of the P and the Q, and I put it like that.
Yeah, you can.
So then one internal line there becomes two internal lines, the other line. And similarly for one.
Yeah, I don't know how far you can take that intuition, but at this stage, yeah, you're completely correct. You can think of it as you've introduced some Q, but because of momentum conservation, the Q gets fixed to be what it needs to be on this pole, particular pole. Yeah. Okay. All right. So all this to say that in general, once you start putting these together, the integral representation of that amplitude now involves delta functions that look more like this. Okay.
So this is a black white diagram to come to the residue.
Exactly. Those are the residues. In this case, we had only one diagram, so the residue is the amplitude. Yeah. But otherwise, you're right, it will be one residue, so you have to sum over the residues to get the final answer. Yeah. So good. So now putting these W and B matrices together, you can rewrite the whole amplitude in terms of this C matrix. Okay. Now C is a K cross N matrix, and for N equals 4 super Young-Mills, it was shown that C belongs to a particular class of matrices called Grassmannian Kn. This is just the space of K planes in n-dimensional space, but in particular, if you do an adjacent shift, you get this G plus Kn, positive Grassmannian. So all consecutive minors are positive. So this is why people say that N equals 4 has this auxiliary positive geometry structure, because when you write it as an integral over C, C belongs to a positive space. Okay, where positive is defined in this very clear way that consecutive minors of this matrix are positive. Now, K cross N matrix, already you can see that it is just a K plane in n-dimensional space. It's just telling you what the K basis vectors are, right? And then because it's a plane, you don't care. I mean, the plane is specified by any K basis vectors plus a GLK rotation won't change which plane you're in, right? Which is why when you actually write down what the amplitude is as an integral, you get this volume GLK and the minus. So this is the representation, integral representation of not just the 3-point amplitude, but any n-point amplitude. Okay, where K is nk minus 2 MHV. So this is not my work at all. This was done in 2006, I think. Yeah. So it's been around for some time now. Yeah. Okay. Good. So now, of course, I told you that C belongs to G plus. This positivity structure only exists when you do an adjacent shift. So the first step will be, let's do a non-adjacent shift and see what happens. What kinds of C matrices do we get?
So please say again, what question you're trying to answer?
The question I'm trying to answer eventually is a question of how do you understand non-planar on-shell diagrams? That's the sort of overarching question. But all non-planar on-shell diagrams, study all of them at once is difficult. So instead, what I'm doing is studying a subset of non-planar on-shell diagrams that come from BCFW. So I already showed you how BCFW gives you some subset of on-shell diagrams. Now we're going to see when I do a non-adjacent shift that I get a subset of non-planar on-shell diagrams, and I will tell you how to construct those because I know how to do the left-hand side, which is just the tree level amplitude. The physical question is?
That is something that you can define.
Yeah.
At the end of the day.
So you could think of it in two ways. One, just one, you could you could listen to this talk and be like, okay, this is just another way of calculating tree-level amplitudes.
This is important.
But
BCFW program for your units arrest
no, it's the opposite. We're using BCFW to understand non-planar on-shell diagrams.
The non-planar on-shell diagram is something that you introduced, right?
Well,
The black dot and the white dot.
yeah, they automatically show up if I do cuts of non-planar loops.
Like, don't introduce this. So if I want to go back to the picture. Yeah, if I just take to this kind of picture there on the left, not these black white bars.
Yeah.
Then I can just construct BCFW.
Yeah, absolutely. You don't need to. So this is not helping me do BCFW. BCFW is going to help me do this.
And with that, what?
So with this, these are planar, but in the case of non-adjacent shifts, you get non-planar diagrams over here. And because I know what this is, I'm going to give you now a way of understanding what the non-planar diagrams are. And these non-planar diagrams naturally arise in cuts of loops. So it's giving you
this loop amplitude. When you try to apply BCFW to loop amplitudes, you would have to learn this, right?
Unitarity cuts. Yeah. So if you were to start calculating loop amplitude, the unitarity cut would give you non-planar on-shell diagram. And then be like, okay, how do I calculate this non-planar on-shell diagram? So we are giving you a way of calculating non-planar on-shell diagrams, some subset of non-planar, not all of them, some subset of non-planar on-shell diagrams.
So even if the unitarity cut to, some diagonal diagram.
Yeah.
I will not get any.
You'll get a tree, of some kind, and that you can write that. So if you take any loop amplitude and you do a maximal cut, you'll get an on-shell diagram.
Yeah, we should.
May or may not be plain. That depends on what is the diagram you cut.
Oh.
Yeah.
If I don't work with this black white one.
Yeah.
Then
the tree amplitude is planar.
Yeah.
Then the tree amplitude is planar. Sorry. Correct. No, so I think so in the planar limit, I think you're correct that you just get something that is tree-level and planar. I think something more complicated happens when you're in a full large end. Because when you can get these non-planar on-shell diagrams when you do cuts of loops. Those are, I don't know whether to call them tree-level. They are on-shell diagrams. They are not amplitudes as such. So we can talk about it a bit more, but yeah. It's, yeah.
When you cut a loop amplitude.
Yeah, so you're.
You would get
No, I understand your question. You're saying that if I cut a loop amplitude, I should get tree-level amplitudes. Tree-level amplitudes are planar. And so you should, yeah, that is what you're saying. But you do get non-planar on-shell diagrams when you do these cuts. It's not, I don't know. Yeah, I don't know how to square it with your question. I don't know how, yeah.
Is it the difference between G and square permutation theory versus monovariant permutation?
I think it's some subtlety related to that, because when you do the actual loop, when you glue things together, you should have a factor of n, right? When you do the color sum in a loop. So but this is why I'm not entirely sure how exactly the unitarity works with the n expansion. With the cuts, whether you get, I'm not sure. Yeah, sorry.
I'm just saying the tree graph problem.
The tree graph is the tree amplitude is always a planar amplitude in the end of the day. But these, so I don't know why this is true, but I know that it is true that when you do cuts of loops, you get non-planar on-shell diagram generically. Yeah, I'm not I'm sorry, I know I didn't answer your question, but yeah, you do get these. Yeah, that is the motivation, because otherwise, why would you study non-planar on-shell diagrams? But they show up in these cuts. Yeah, they do. But I know I didn't answer your question, so I'll think about it a bit more. Yeah.
When I see that, when you do black and white things, and then you will maybe cut and then you might get wrong, but I don't know what it means actually for the matter.
Yeah.
But
Yeah.
that's good for it.
Yeah, I'll think about it a bit more carefully. I'm also now a bit confused. Yeah. But anyway, so the rest of this will not be about loops again. It'll just be about non-planar on-shell diagrams. Yeah. Okay, so we have this formula, and the idea is what happens when I do a non-adjacent shift. So, all right. Let me skip a few things, which are details, doesn't actually matter to the story. So right now we have looked at the following. We saw that you have, for MHV at least, for adjacent MHV shifts, one BCFW term looks like this on-shell diagram, and which there's some associated C matrix, right? Which is the integral that you're going to do. You do the integral and you get an answer. You know what the answer is. The answer is Park-Taylor amplitude for MHV Yang-Mills. So you already know what the answer is. Okay, good. Now, few things to notice here is that the Park-Taylor amplitude, and this sounds very trivial for MHV, but bear with me for the moment. All of these poles are all in lambda. Okay. So it's just lambdas going together, hitting one another, becoming collinear. These are the only types of singularities that exist in the tree level amplitude. So this is the property that I'm going much physical weight to the property, but it exists for MHV. Okay. So in words, this is what we had. We had some BCFW on shell diagram. It was related to a C matrix that lived in this space, and that gave something with holomorphic poles. Okay, so this positivity and holomorphicity is what we want to see, whether that continues beyond this planar sector.
If you take the two pluses and all minuses, they end up this bracket. Two minuses and all.
Yeah, so when I say MHV here, I'm going to just stick to meaning minus minus plus. Sorry. I'm going to stick to meaning two minuses rest plus. And what you are saying is that MHV is also two pluses and rest minuses, but I won't call that MHV. I'll call that N MHV. Yeah. Okay. So yeah, but you're right, obviously, that you will get the square bracket structure, but I want to write even that amplitude in terms of angle brackets. I want to write all in terms of angle brackets. Okay. All right. So what is the C matrix and how do we think about it? Okay. Now, the rest of this talk is just going to be how do you visualize the C matrix, and the C matrix will then give you what the amplitude is. The C, then show us the C matrix. Okay, this is the C matrix. It's just a K cross N matrix, which I'm integrating over. Okay, and so what do I put in here so that I get the correct amplitude out? C matrix looks something like this.
And what are the alphas?
So the alphas is some way of parametrizing the solution to the constraints. So you have these delta functions here.
This was solving the delta function. Alpha.
So I take a C matrix, I parameterize it in some way. The way depends on what I'm calculating. So like every on-shell diagram, there's a way of getting a C matrix out of it.
I could do integrating those.
I am. So this is, but okay, what C means over here depends on what is it that what I'm calculating. No. So it is this in particular. I parameterized it. Now I can solve for alpha.
Now you integrate over the alpha.
Yeah. Now I can solve for alpha, integrate, and I get the answer. So that's behind the scenes what's happening.
The number of alpha seems to be the number of cooperatives.
Yes. That is okay, but okay. So that's also because there is a GLK sitting here.
I see.
Yeah, and also when I say K cross N, it's not necessarily full dimensional. Yeah, so it is full dimensional. Oh, yeah, it's not necessarily full dimensional. For BCFW, you get some particular dimension. Yeah.
So this is not a natural way of.
No.
Some of the values.
Yeah. So basically every on-shell diagram gives me a C matrix. I put it back in here, and then I get the answer out. So this is just a way of getting when going from whatever this integral formula to the actual amplitude.
This is the recipe which are given by this black, white dot diagrams. For those, each of those diagrams, when you solve the delta function, there's some unfixed thing which you will be able.
The integral will localize. So once you solve the constraints, there won't be anything left. Yeah. For BCFW, for tree level BC, for the residues that you're talking about. Yeah. So there is no extra content in this equation.
That's how when you have written the DW.
Yeah, exactly. There was nothing extra. So this is the same thing, except now you put all of those B and W together. That's how you got this bigger equation.
Why don't I just work with the localized expression because they get all tangled up?
Yeah, so the reason is, yeah, that's one thing. So you'll see that actually once I start thinking about this C matrix, there'll be a very easy way to look at this. So this is a visual representation of C matrix. I'll tell you why. But once I look at this, I know what this means, and I can just write down the answer. Okay. So now, if, for example, like we'll start looking, once we do NMHV, we'll start looking at pictures like this, and I can just on the blackboard now tell you what this is. And then the amplitude is a small sum over this, and I will just be able to write down the amplitude, any endpoint, any K point. So there is a simplicity that arises after you go. I know it looks like you're just making your own life harder, but eventually when you look at the C matrix and the geometrical way of constructing the C matrix, everything looks much simpler than it would if you were just doing. Yeah. Also the tree level BCFW doesn't work at loop level. So it doesn't give you cuts and things like that. Okay. So I know I have sufficiently complicated BCFW, but we'll see that there is some nice simple structure that's going to come out. Okay. And the way that we're going to see that is, so C is a K cross N matrix, right? And I said that this is K n-dimensional vectors, but you could also look at it as n k-dimensional vectors. K is this, and K minus 2 MHV. Yeah. So right now K equals 2, because I'm just looking at MHV. And so, yeah, so this is a 2 cross N matrix. Okay. And it's, yeah, so instead of looking at it as 2 n-dimensional vectors, I'm going to look at it as n 2-dimensional vectors. But also, see, actually, the vectors live in projective space, because let me just write this here. This was the delta function. Okay, so lambda has some little group scaling, and so you can always fix one of the components of C. Okay. So this means that if this is P1, this line over here, then each of these will just be some point on P1. Right. In addition, because C belongs to G plus 2n, the minors are positive, which means there is an ordering. This is a convex configuration of points in P1. Right? Okay. So, all right. Now we know that finally, once I evaluate everything, I'm going to get this as my answer. So, okay. Here, when I talk about C, it belongs to a real space. Yes. So technically, C, I mean, the way that I introduced it belongs to complex Grassmannian. But there is so right now I'm just going to be talking about minors and positivity, but there's a sort of analogous way of stating it just in terms of linear dependencies of vectors. But but we'll just be talking about positivity of minors. Yeah. Just they are all real numbers, right? So this is, I mean, direct statement that positivity of the minor says that these are ordered in this way. Okay. And you know that it gives you this holomorphic form. Okay. And the way to see that from this diagram is the following. So you're saying that the only singularities of the geometry happen when points run into one another. So 1 and 2 merge, or 2 and 3 merge, etc., etc. Those are the boundaries of the geometry. And you can see those are exactly the poles that you get over here. Okay. So all poles are given in this way of boundaries of the geometry. So now what I'm saying is,
what's going on?
Yeah,
That you press the button.
yeah.
So I
Mm.
actually doing it in the, I thought you were saying at some point that the delta function completely local.
So good. So when I say do the integral, what I mean is that these will solve some constraint equation. If I solve this, actually for MHV, C equals lambda. So like literally C equals lambda. So minus just our angle brackets. So when I say that these two come together, what that means is the minor 1, 2 goes to 0, right? Minor 1, 2 goes to 0, which is angle bracket 1, 2 goes to 0. Yeah. So you've just made a geometric picture that captures all the singularity structure of your amplitude. Yeah. And at MHV, that's the simplest case is MHV for adjacent MHV. Okay. So now what we want to do is go two things: adjacent NMHV and then non-adjacent MHV and NMHV. Okay. And because of the simplicity of things, we'll hopefully get through these slides somewhat quickly. But we'll see how simple it is or not. Okay. So for NMHV, we have two types of BCFW terms. Yeah, you have this one and you have this one. So this is two MHVs come together, and this one is the lower point NMHV with the MHV bar. Okay, these are just the two possible terms that you have. Here you can think about 1, 2, and 3 as being negative and the rest being positive. Right, so that's how you get it. Yeah, you have to be a bit careful. Anyway, okay. So each of these will now correspond to an on-shell diagram. So this becomes a sum over on-shell diagram. We saw that this becomes also a sum over some types of C matrices in G+3n, right? Because each of these diagrams gave us a C matrix. And so, yeah. And then finally, we also saw that each C matrix looks like some picture like this. So this is P2 now for the time being, this slide. And so now a generic configuration of positive points is this convex configuration over here. Okay. Now, in particular, BCFW always gives you this codimension n-5. Okay, this comes from just the counting of constraints versus how many vertices, that kind of thing. Okay, so which means you have to put one constraint at 6 points. So you get these three on. So basically, there are three on-shell diagrams. Each of them correspond to these three configurations. And so summing over that gives you three contributions, and that is just the 6-point NMHV amplitude for Yang-Mills. Okay, where these are called, it doesn't matter, but they're called R invariants, and this is how they're defined.
I'm understanding very little, Shruti, but this is reminding me of the whole Witten stuff.
It's very similar, yeah. He does it in twistor space.
Yes.
Yeah, which crucially we don't want to do because at some point we want to get rid of the external ordering. So this is like the kinematic space version of that full thing. Yeah. Yeah. Okay. So you get these R invariants, and here you can clearly see that there are poles that don't look like just angles coming together. So how do you see that? How do you get the holomorphicity back? So the first term we saw was MHV times MHV, right? So that is just literally take this one MHV amplitude on one side, take MHV amplitude on the other side, and times the 1 over pole, the pole, 1 over p square. That was what the BCFW formula told us you have to do. Okay. Now, nicely, you can actually rewrite this pole term as a 3-point, where is it? As a 3-point MHV amplitude. PT means Park-Taylor. So I'm going to replace this by a 3-point amplitude. And I'm going to add some things in the numerator so that this actually is a 3-point amplitude. Okay. And what we find is that you can now write NMHV as MHV times MHV times MHV instead of times pole. Okay. So there is this now very simple picture that comes about, which is these 3 lines like this. Okay. So I get these 3 lines and I know how to interpret the lines because this is an MHV amplitude, this is an MHV amplitude, that is an MHV amplitude. And that is exactly what we get out. So this is one of the contributions to MHV and it is Park-Taylor times Park-Taylor times Park-Taylor, MHV, MHV, MHV. Okay.
What was that about the pole?
So the pole, so this is this pole over here, I have just replaced by an MHV amplitude, a 3-point amplitude. So I mean, in some sense, all I'm saying is that the ratio between this and this is that. Okay, I have just moved my terms around so that I can rewrite it as looking like a 3-point amplitude. Yeah, but it's.
And is this stuff also, there's this also business about it, integrating over a world sheet.
Yeah.
In some form over a world sheet. Okay.
Yeah.
This is reminiscent of that as well.
No, I don't think so. At least I don't see a direct correlation.
What I was thinking was that he also had these forms that were delta functions.
Yeah.
And you were integrating and they got localized.
This is true. At that level, you're right, but I don't see a direct comparison over there. Partly because there's no sum over diagrams that you do at all. It's just a formula. What Shiraz was talking about was CHY. Yeah. Okay. So good. So you can take this picture seriously in the sense that in the following way that this, once I draw this, it means that it's a product of Park-Taylor factors, and that's the term that I have to add in to the summation. The second term involved a lower point NMHV, and we find that this diagram just is the same as taking the 5-point diagram and adding 6 between 1 and 5. Okay, so you can just literally evaluate this, and check that this equals this. So now this allows you at any endpoint to draw this diagram and say, now I sum over all possible configurations that look like this, and that gives me the NMHV amplitude.
Just in one case, I want to translate the diagram to.
Okay. That you would.
Is that a bunch of lambdas in the denominator?
Exactly this.
And that was a bunch of lambdas
in the denominator because they were all MHV amplitudes. So the thing is, you have rewritten your NMHV amplitude as a product of MHV amplitude, which means all of the poles, even these ones, are now going to look like angle bracket poles. Yes. But they will involve these 2 spinors sitting over here, I1 and I2. Actually, this is the next slide. So I1 and I2 I've now defined in some way, and now all of my pole structure is just given by MHV amplitudes that now involve these new spinors I1 and I2.
And I1 and I2
I1 and I2 are given over here, where P3 is the sum of all these momenta, P1 is the sum of all of these, P2 is the sum of all.
So
sum of this is a sum of momenta. P3, P2, and P1 are sum of momenta, and this is an angle bracket. So these are spinors. So this gives you a spinor for lambda I1 and lambda I2. Yeah. Okay.
Okay, so this is very direct translation.
Very. So actually, I mean, if you really didn't want to think about the C matrix or anything like that, you could just say this picture gives me this. Yeah. So I mean, eventually you want to be able to go back because you want to be able to connect this to some picture, some like on-shell diagram. But otherwise, you could just do this.
Our point is that those poles that you see in the CFW are these diagrams.
Yeah.
With various distributions of.
Yeah.
Some more.
Yeah, exactly. So if I sum over where I stop on this line, where I stop on this line, that's all possible configurations. And sum over that is exactly the sum over BCFW term. So each of these is a BCFW. I had two types. One is this type. So here it's indexed by I. And then one is this type. Each of these will be a sum over thing. So yeah. So it's not a one-to-one correspondence. But yeah.
You go one up.
Yeah. So this I is the same as yeah. So this I is the same as the MHV times MHVI, but the J is yeah.
So suppose I didn't know your method, right? You gave me the answer, I could check that it has all the singularities that I think.
Yeah.
And it's a manifest from some. Only once you put it together.
Yeah, I mean the boundaries of if you think about this, the boundaries of the geometry are when the points hit one another.
And that will be the singularity.
In a sense, you do pictures was to make it singularity.
Yeah. Exactly. You introduce the picture so that it's easy to see where the singularities are, and also that now you get this expression where all the singularities are just in lambdas. So you don't have to think. R also, yeah, exactly. So now I've rewritten that R only involving. It's the same R, and that's crucial actually, that you get the correct answer. To get the correct answer, it has to be the same R as before. And it indeed, you can check that if I just made this a 6-point amplitude, this would be the same R as I showed you a couple of slides ago. Yeah. Yeah, I'll show you at the end. We have like a few pictures. They're somewhat poorly drawn, but you can still see that. Yeah. So obviously it gets harder to visualize as K increases because the dimension is increasing, but P2 is the easiest place to see. Yeah. Okay. So good. Let's skip. Let's get to.
Then I guess I go understand distinction and what is the difference between pole structures for the MHV?
So
MHV just things are on the line. So you have these closest guys coming together.
Yeah.
Right? But now for the NMHV, why is that different?
NMHV also.
Why is it that the one that is given by this triangle?
Yeah. Because in some sense you have said this is the geometry. So it depends on like how you are.
Why the poles are not expected when within particles something like that.
So even physically, if you have an NMHV amplitude, it's still color ordered.
Yeah.
So only stuff that is close by.
Yeah.
In some broad sense, only stuff that's close by can make a pole.
Yes.
So that is one thing.
Triangle is telling you something more, right?
Triangle is telling you something more. I mean, triangle is capturing all of the poles that should be there. I mean,
But that is different from them just being on a straight line.
Yeah, it is.
Yes, what is that difference?
The difference is the fact that you don't just have two particle poles, and that is basically the statement that for MHV, when I wrote this BCFW term, there was only one which was a two particle pole. But this one has a I particle pole, and here it also has a two particle pole, but it has an I particle pole as well. So you have to make sure that you get that somehow, and that is what this is doing.
Because the capital I and I do somehow the sum of all these things.
Right.
Collision of that there would be like an I particle.
Yes, exactly. Yeah. So in that sense, it's somewhat non-trivial that you can just do this. Yeah. Okay. So now let's do non-adjacent. And you'll remember non-adjacent, even for the MHV case, you had these two diagrams, right? Because K could either be with K minus 1 or K plus 1. All right. Now, no longer do you find that everything will respect this ordering when you draw the line. Okay. But it's a line. So you can always order the points. I mean, it's just a question of what are you saying this is ordered with respect to 1 through n, then it's not. But if it's ordered with respect to 1 to k minus 2, k minus 1, k, then it is. So you can always, for any line geometry, you can always find a way to say that, okay, it is convex with respect to some ordering. So lines are a bit trivial in that sense. Okay, and obviously, if I write down the Park-Taylor factor for this, it's holomorphic. This is just the MHV amplitude. The MHV is a bit trivial. The real like meat comes from non-adjacent NMH. Okay, so that when you do that, you get, so this is the easiest example, which is 5 point. You get these two diagrams. You don't get that other green guy because there is no 4 point NMHV. So this is the only two BCFW diagrams for 5 point. Okay, now I draw what I expect to happen, which is 1, 2, I. So that's a line MHV. I 3, 4, 5. So I 3, 4, 5. You could have put 5 on that side also, it's projective. And then the pole term, which I told you could replace with the 3 point amplitude. So 4 hat 4 1. Similarly over here. So now very clearly.
But not similarly. I mean, now from there I should be able to see that, right? That's the point, right? Now from this left diagram, the triangle diagram, I should be able to see that unity out. Isn't that the case?
Why so?
I thought that triangle diagram encodes everything.
No. So this is two BCFW terms, right? So even in this case, we summed over the diagrams. Yeah. So I'm saying there are two triangle diagrams that you have to sum over in this case. One of them is this one, the other one is this. Yeah. Yeah.
In the MHP, when you have this diagram, we had 2 and 1 going to everything else. But was that diagram giving you that diagram was producing what whole?
The colony, well, okay, that is one. Do you mean the Feynman diagram or the BCFW? All the poles.
All, right. The fact that specialists chose those two
didn't matter. No. Because there's only one BCFW term. In this case, each kind of has a subset. So this will have some, this will have, and together they will give you all. Yeah. Okay. Good. So in this case, I can't just change the external ordering and say it's convex. It's some genuine non-convexity that arises in this case. Okay. And just to show you, like, this would look like this. So these non-convexities, they do look like non-planar on-shell diagrams. Okay. But okay, what do you do with these non-convex things? So generically, you get this. Okay. You can write the NMHV amplitude as some sum over these non-convex configurations where now I have points here, I have points here. This is the most, this is
quite a different way, right? But I have already known the answer because I
exactly. Right. Exactly. So I know what this side is. Now I want to make sure that my natural interpretation of this side, which I mean, all of us might have the same guess, which is like you do MHV times MHV times MHV. But that is still a, you're hoping that is correct, that intuition holds, and we'll find that actually it does. So if I sum over this, thinking that all of these are MHV, I'll get exactly that on that side. And I know what that is from multiple other methods.
That's like moving these lines.
And yeah. So it's a little more than that. So let me just say that, so maybe what you had in mind is you take this and you join it with that. Yeah, so it's not quite that. Yeah, so it's a little more involved than that for the simple reason that you see, then you lose the information of what is I.
Right.
Yeah, so it can't be so simple. Yeah, so what you do, what happens instead, or rather the way that we approached it is, so what you want to do is you have something that is non-convex. Can I write it as a sum of convex things? Is where we are going. Okay, and so to do that, we use these relations, which you might remember from a couple of days ago, the Kleist coefficient. Just that, okay, if these weren't there, the points would be a convex configuration, right? I mean, they would, yeah. So it's non-convex in the sense that now these points are no longer positive in the sense that they were before. So if I took a minor of I, L plus 1, M, that would be negative. Yeah. Okay. So you remember that I told you that color ordered amplitudes satisfy these types of Kleist-Squish relations. Okay. So basically what do Kleist-Squish relations say? Some ordering looks like some other ordering. Basically, or a sum of, in this case, a sum of other orderings. So in particular, they conveniently work out so that I can rewrite this ordered MHV amplitude as a sum over of orderings where all of these points are on the inside. Okay. So each of these, I can now take all of these points and go inside, but I have to now sum over some permutation. Okay. Basically this. So now I've taken the points that sat over here inside, but I have a sigma I have to sum over. Taken the points over here, move them inside, but now I have a sigma that I have to sum over. Okay. Given that this is true, now I have two ways, in fact, of writing my amplitude. One, I can just take this after doing this step and say MHV, MHV, MHV. Or I could have done it directly, which is saying that this is MHV, MHV, MHV. Okay. So all this still leads you to the correct NMHV BCFW configuration. So you have these non-planar, what we are calling Grassmann configurations, and they give you, and you know exactly how to interpret them as a product of Park-Taylor factors. Okay, good. So this was the promised higher dimensional case. So it's not, I mean, it's actually not that bad looking, right? I mean, you kind of look at it and it looks very similar to these things. Just have a different, you just have a larger number of lines. So now you get more Park-Taylor factors. There's literally the number of lines. 1, 2, 3, 4, 5, 6, 4, 5.
What is there a good sheet for this?
Yeah.
Is the directive convex?
Yeah, 1n. So adjacent always gives you convex configuration.
And what is the picture?
The same, except now you don't have points here. Yeah. So on the outsides.
That those points.
These. So you get like a box. Some shape like this. Something like that, I think. Did I draw it correctly? Maybe I didn't draw it correctly.
And that is convex.
I didn't draw it correctly. Yeah, that is convex. So this is a convex thing, right? That piece basically. It's convex. If you do one n shift. Yeah, but because we're doing non-adjacent, you get these non-planar things. And now we have an interpretation for each of the non-planar things.
Just think of each line as not just.
Exactly. Yeah. Okay, so I'm going to end soon. I just wanted to, because I know this can be somewhat technical. So
And again, you summarize what your final accomplishment.
yes, this is what I'm trying to do. First, I'll just point out a few things that came out of this, which were nice, and then I'll try my best to summarize what we got out of it.
Why you should care about it.
Yes, I'll try and tell you why you should care. So so one thing was that in the usual case of just, I mean, forget any Grassmannian geometry, anything, just take amplitudes, just look at what their structure is. And you find that for n equals 4 super Young-Mills, because it has dual superconformal invariants, you have to make things out of what are called R invariants. Okay, and those R invariants have some very nice properties in that they are dual superconformal invariant. That's why they're called R invariants. So in particular, they respect orderings. And here, while we find something that we're still calling R invariants, they are not invariant. We don't know what they are invariant under. Okay, so in that sense, we're just calling them R because their counterparts were called R, but we don't know of any symmetry that actually keeps these R's intact. There is a question there, which is once I go off of once I start dealing with non-planar things, is there any kind of residual dual conformal symmetry? So basically are these objects, kinematic objects that we find. So this I would call a R disordering, right? And so is that actually an invariant of some, I don't know, residual symmetry? So, yeah.
The question is the answer that we're getting. Right, for the adjacent shift, you got some simple thing answer, just be an animation. Right, going for this kind of thing come out. And then you made an attempt to relate that with some more months.
Yeah.
Does that show that this is equal?
So it's actually nice to hear.
When we did the adjacent shift, there was no sum.
Yeah, so it's actually nice how it works out. So here, this Kleist-Coif relation and the sigma and all, I have applied it to each line individually. But that's because I knew that each of these is an MHV amplitude. But the whole thing is an NMHV amplitude. So the whole thing also satisfies this relation. So now if I take this, it equals what I showed you before with the adjacent shift, but it equals it because of the Kleist-Coif relation on NMHV. So you can,
because this is equal to a particular term in the sample.
Yes. So I'm saying that every non-convex configuration is a sum over convex configurations.
So it should be equal.
Equal. Each of these pictures equals a sum over convex pictures. A sum, though. It's not like this equals.
INJ sum, that's what you mean, right?
No, not INJ sum. This one picture with I, J, K, M all specified, L should be here.
But when it is sum over both things, the IJ here and the IJ there, they are equal, right?
Yeah, because that is the amplitude.
The single term becomes a sum.
Correct.
I see.
Yeah.
Okay.
Yeah.
Right. But now, would I be now misguided by this sum because of the sigma, there are permutations. So I would conclude that there are residues coming from some collisions there which are not actually present.
So you find that you get some. I mean, you see that there are some things, but in the end, they're all removed.
So basically, what I want to say, I mean, if I think of this picture that you're getting as being manifestly giving me the pole structure of the amplitude, that's what is nice about it. Let's say. So I want to look at this. Then the pole structure that I would read out from here, and the pole structure that I would read out from these other things, which is the sum over with the IJ things.
Yeah.
They should give me the same pole structure.
I agree, but so that's why I will say that this picture, though it is non-convex, is actually nicer than this one, because of precisely what you said. That here, if you do that pole thing, it's not that explicit what you get. Whereas here it is, but it is non-convex. So it depends on which one you want to.
No, but whatever it is, the finally should come out the same. Right?
Agreed.
And it's clear that this picture and the convex picture will be the same.
Yes, but after you sum.
So what was the sum then?
The sum is over IJ. Yeah. But each of these will only give you a subset of poles. So you are saying, because obviously, if I take I to this side, now suddenly I have I plus one pole that I didn't have.
Sum over I is the whole thing, right?
Yeah. But each diagram gives you a subset of poles. Yeah. So I'm breaking it up so that, okay, there are some non-convex way of breaking it up, and there's a convex way of breaking it up. And each non-convex also I can break up into convex if you wanted to.
There's no direct way of saying that the whole set of poles, I guess.
No.
Then work it out and see that.
Yeah.
Some more IJ, once you some more IJ both sides, it will be the same set.
Yeah.
And what about convex do you like better than non-convex?
What about convex do I like better? I think it's just that has been studied more. I mean, people have done a lot of work about integrands in n equals 4 super Yang-Mills, and all of that involved convex configurations of points. but that's because they were dealing with planar things. So, but the minute they want to start doing non-planar things, they're going to need these non-convex configurations. So this is
in terms of context, just to rewrite it in terms of something.
yes,
Well, this may be the more useful.
yes, I think so. Yeah, yeah,
One of the points that you made is that it's as nice, right?
yeah. In some sense,
What you- right?
yeah.
Because you just read it out from here.
Yes, precisely, and it also continues beyond.
Yeah.
And you said this more manifestly shows you the singularity.
Yeah.
That picture.
Okay. So maybe in the interest of time, let me just summarize. Okay. So yeah. So before this talk, right? Before this talk, there was an understanding that if you did an adjacent BCFW shift, that
This
yeah.
skyscraper relation, does it have minus one about?
-1 to the not power sigma to the power mod of beta, I think. So
Minus one.
they are, it's an overall -1.
Overall,
It's just the size of beta that matters. I probably not, but
I
maybe.
mean, the sigma should go up, right? It's bad or being poor.
What do you mean?
don't have holes, right? I
Where?
mean, one cannot come close to 5.
Yeah.
Cancel.
They have to cancel. Right. Okay. So before we had it was known that if you did adjacent BCFW, that you would get for MHV amplitudes, you would get some associated positive geometry, and all singularities would be holomorphic. This was known. In addition, for NMHV, it was known that you still get a positive geometry. The singularity structure was a bit mysterious. So now what we have done is we have NMHV and beyond, and we can now write them as products of Park-Taylor factors or products of MHV amplitudes. And now we have this very easy way of figuring out what is the singularity structure even for NMHV and beyond amplitudes. Okay, that's the first thing. The second,
Wait,
yeah.
Can I summarize that you've got a better way of writing down the answers for non-MHV? Yeah.
yes,
So that's a great motivation by itself without saying any of this concept.
that's right.
Okay.
That wasn't our motivation going into it. So maybe I should present this differently the next time I present it. But you're right. This already is a useful thing, in my opinion. Yeah. So
Convex diagrams were not.
the convex part, the fact that you could write down some convex thing was known. But
This non-convex.
yeah. So
And equal.
yeah.
Something with the whole shot more manifestly.
Yeah.
I mean, convex also will solve all the holes.
But you have to do some sum.
So okay, normally, right?
But I thought you got spurious polars in each term of the convex thing, which went away.
Yes.
No, the sigma only.
No. So sorry.
No, I think
Each BCFW term has some spurious poles. Each BCFW. So then each BCFW term will give you some Grassmannian configuration. That Grassmannian configuration will faithfully give you all of the poles that BCFW gave you, including the few spurious ones.
And that's true for both your representation as well as
yeah. So, but okay. So one thing that is new is that this convex configuration, right? It normally you would be like, okay, this is my C matrix. Now I put it into that formula and I do the whole thing. And oh, what do I get out? I get something out. Okay, fine. But this, you can sort of surpass all of that. I draw this picture, I write the term down. Yeah. So there's some simplicity there. Okay. Now, additionally, it also, even though when you do non-adjacent BCFW, you get these non-convex configurations, we still have a way of interpreting that in the same, along the same lines as products of MHV amplitudes. Okay. And in some sense, all I'm doing is taking the tree level amplitude and breaking it up differently, right? So I've given you just new objects to play with. I've said that now there are also these non-planar, or whatever you want to call them, non-convex Grassmann configuration. They are also nice for these reasons that you can write them as products of MHV amplitudes. And individually, so as a sum, they give you the tree level amplitude. Individually, they could possibly appear on cuts of loops. So that is, yeah, I think that is a somewhat reasonable summary of what we hopefully accomplished in the last few minutes.
So first we found a new representation for non-MHP amplitudes. And second, there's a hope that that reduces.
Yeah.
Any questions? There were a lot of questions during the talk, but maybe for gravity, how much of it
Okay. Actually, that's we're thinking about that now. And it seems like it goes through. So one thing is gravity, you don't need all this on the outside because the MHV amplitude itself doesn't care about this ordering. So this is anyway some mixed thing. So being on the outside or inside of this line doesn't matter. Yeah. So that's the first thing. So all of the configurations look like this. But in addition, if you look at the
by all that, there also one can talk about MHV.
yeah.
There also
For n equals 8.
N to the K thing. Yeah. You will have these vertices kind of I1.
Yeah. So you do the same thing, you write down the BCFW terms and you get some sum over configurations. Now, the thing is, the question is, how do you go from the configuration to the term? Okay, and if you check just simplest thing, so just check the mass dimension of MHV times MHV times MHV for a gravity amplitude, it won't match. So you have to dress each of this with something else. And we have a guess for what that is. Seems to work, but we've checked to like 5 point. So it's still a bit preliminary, but it seems that there is a way of writing down. And there it's actually, I think, much harder to do the BCFW expansion in gravity. So it would be very useful if we could do something like this over there. Yeah. So, but it looks very similar with just some pre-factor outside of, so it's like MHV times something.
When you say gravity, you mean linearized?
Yeah, I mean perturbative linearized Einstein-Hilbert action. Yeah.
So gravity are you using double copy to make the dimension?
No, actually that's a whole separate question, which is, can you take this, somewhat double copy it to give you the ones that we're finding in gravity, which there's no reason for it to work also. Because the double copy works at the level of the amplitude, not pieces that you construct the amplitude with, right? So you can't take each BCFW term and double copy it. It doesn't work like that. Yeah. So I mean, that's a separate, that's also a different question you could ask, which is, if I took every single BCFW term and I double copied it, does that make sense? Does that give you the BCFW expansion of gravity? Actually, I don't know if anyone's looked at that.
You had a point saying that double copy works nicely with BCFW. That's not what it means.
It does, but I meant the scaling.
The
The scaling, yeah. But not the expansion itself. Yeah. Yeah.
All right, no more questions. That's actually again.
Okay.